Hello and welcome to another Reigate Maths video. In this video we're looking at the probability chapter of the first year statistics module from the Edexcel Maths syllabus. My name's Simon, and in this video we're going to be looking at introduction to probability distributions, looking at some definitions, and then looking at some discrete distributions. So what is a discrete probability distribution? Well, we need to look at some definitions first. The first one, and it's key to a lot of what you'll do in statistics over the 2 years, is the idea of a random variable. So this is a variable whose value depends on the outcome of a random event. Typically, we'll use uppercase letters for random variables, most commonly X or Y. And what we'll do is we'll do something like this to say, okay, what is the probability when we have a certain number of occurrences of our random variable? So if this little x was 3, we'd be looking at the probability of this random variable happening 3 times. Okay? Or if it was something different, so if it was like x represented the height, we would be looking at the probability of the height being 180 centimeters or something like that. The random variable can take can have a lot of different meanings, but it's a construct that we need in order to do the maths. So in an experiment, a random variable can occur a certain number of times. So let's think about rolling a 6-sided die. So the possible outcomes are little x, and the chance of that outcome happening is the probability of our random variable capital X being equal to the number that we roll. Now, typically when we start talking about this kind of probability, we need to define what X is first. So we'll say let X be the number rolled on a fair die. Something like that. So this first row in our table is the list of possible outcomes. So if we have a fair 6-sided die, the possible outcomes are 1 through to 6. This is a discrete distribution because we can't roll 1.5 on a die. It doesn't make sense. The bottom row is the chance of each thing happening. So if the dice is fair, the probability of each of them happening is 1/6. This is what's known as a probability distribution because it describes the probability of all outcomes in what's known as the sample space. So the sample space is this row here. The sample space is the range of possible outcomes. Okay? It has to be all of them, so if we just labelled 1 through to 5, that wouldn't be the sample space because we're ignoring the possibility that we could roll a 6. So that's kind of a core concept of this. It's something that you're not going to have to worry about tremendously, but it's an important idea for probability distributions. As we said, this is discrete because you can't have 1.5. For example. So therefore it is discrete. In the second year, we look at a specific continuous distribution. The variable is random, which is very important for kind of experiments. The variable is random if we don't know the outcome until the experiment happens. So if we roll a die, we don't know which one of these outcomes it's going to be because the die is fair. So X is definitely random. This is also very important because if you're doing an experiment and a variable is not random, well, you know what the outcome is going to be, so it's irrelevant. So we can describe our distribution in one of three ways. This is the first way, using a table. The second is using a graph, where we have the y-axis as the probability, so the bottom row of our table, and the x-axis being x, our list of possible outcomes. And in this case, every single bar has the same height because the probability is the same. So a discrete distribution we write or we draw as a bar chart. There's no curve, so we can't, link anything like that. But this is a graphical representation. The last type is using something called the probability mass function. Okay, and this is where we write the chance of X happening is a certain number, and then we list the outcomes there. Now, strictly speaking, this is incomplete because we know that X is a sixth, or the probability is a sixth here, but the probability is 0 otherwise. This is often used for completeness, but generally you can ignore it. This is a specific type of discrete random distribution because all of the probabilities are the same, which makes this, in addition, uniform. What we're going to do now is we're going to look at a couple of examples where we are going to look at different random distributions. So this is what we're going to look at here, a very straightforward example, flipping some coins. So the first thing that we're being asked to do is write down all the possible outcomes when we flip 3 coins. Now there are lots of different ways to kind of start writing this, but it's just easiest to start listing them. So we could get 3 heads, we could get heads, then tails, we could get heads, then tails, then heads, or we could get 2 tails and a head, or 3 tails. So we have 8 possible outcomes, and this is listing them there. The important thing is now what we do with those. What we're going to do now is use the outcomes that we wrote down with this new piece of information, that a random variable, x, is defined as the number of heads when 3 coins are flipped. So it's relating to what we've just written down. We're going to write down the probability distribution of x first as a table, then as a probability mass function. Typically, you will only be asked to do one of these, but personally, I find the table the easiest and the PMF the hardest. So if I'm going to do a PMF or a diagram or a graph, I generally write a table out first regardless, because I find it's the easiest way to think about the possibilities. So first off, our second row we know is going to look like this because it always does. And our top row is there. The key thing is to think about what this little x is. Little x is the number of heads that we get. So capital X is the number of heads. Generally, lowercase x is the specific number of heads that we want the probability for. So we list the possible outcomes in our sample space. Now these are not what we label here, because little x is the number of heads. So we could get 0 heads, we could get 1 heads, we could get 2, or we get 3. Those are the possible values that this little x can take. 0, 1, 2, or 3. What this says is the probability of a certain number of heads happening. That's what this is saying. So for our first column here, we're going to write down the probability that we get no heads. Out of all of our possible outcomes, there's only one that has no heads in it. So the probability of getting 0 heads for this experiment is 1 out of 8. The probability of getting 1 head is 3 out of 8. 2 heads, again, 3 out of 8. And 3 heads is 1 out of 8. This is our distribution for x written as a table. Now something really important to notice is look at the bottom row. These are all of the probabilities of all of the possible outcomes. And we can see that if we add them all together, we get 1, which is very, very important. If it doesn't add up to 1, then something's gone wrong here, or you haven't listed all of the possible outcomes. The last thing we're going to do is we're going to write this distribution as a probability mass function. So we have, looking at the chances, we have 1 out of 8, 3 out of 8, and then any other opportunity that's outside these intervals. So the probability that x equals little x is either going to be 1 over 8, 3 over 8, or 0. When it is 1 over 8, what are the little x values we've got? 0 and 3. So we list those here. It's 3 over 8 when x is 1 or 2, and it's 0 otherwise. So any other value of little x will give a probability of 0. If little x is 1 or 2, it gives us probability 3 over 8. And if little x is 0 or 3, it gives us 1 over 8. And that's how a broader PMF works. So for this second example, we are given the probability function, but it's got an unknown in it. We can see the probability function is proportional to the number of successes, or the value of little x, because it's got the k in. Now, part A, we want to take this function and display this information as a table. Now, just because this has got some k's in it, the table, the layout, still stays the same. We still have lowercase x as our top row, and probability of capital X equals lowercase x on our bottom row. Now we already know the possible outcomes. What x could be 1, 2, or 3. So we're told what our top row is going to be. Now we know that this formula is k times whatever number this is. So for our first column here, little x is 1. So the probability is just k. Second row, x is 2. So we know this is going to be 2k. And likewise the last one, 3k. What we're going to do in part B is use this table to find the value of k. And this relates to the information that we saw in the previous example. The fact that the sum of all of the probabilities must equal 1. So we know that k plus 2k plus 3k has to equal 1. So k is a sixth. Which means that if we wanted to, we could write out a new table. And when I write down the part C, it's going to be useful there. So I'm just going to write it down to the side. So the probability of having one success is a sixth, having two successes is a third, and three successes is a half. Okay, because it's k, 2k, and 3k. So with our part C, what we're going to use is that we're going to use this information to find the probability that x is greater than or equal to 2. Now for our table, or for our distribution, we know that this is going to be only 2 outcomes. So there's a couple of ways we can do it. Now with this one, with this particular example, either way works fine. But with other examples where we have more outcomes, you may want to do one over the other. So the first thing we can do is go, okay, probability that x is greater than or equal to 2, well, capital X, or this number, has to be an integer, because again, it's discrete. So the chance of this happening has to be the probability that x is 2 plus the probability that x is 3. Because those are the possible outcomes. 1, 2, or 3. We want greater than or equal to 2, so we only want these two. So we know it's going to be a third plus a half, which is 5 over 6. Now this method is fine for this example, because we don't have many outcomes. But with a bigger table, this could become quite onerous to do, and could take a long time. So we know that the probability that x is greater than or equal to 2, we've only got 3 outcomes. We want these outcomes, which means we don't want those ones. Now I'm going to be a bit general here, but then we'll make it specific to this question. We want 2 or greater, which is the same as 1 or less. Okay? Because we want 2 or greater, that's the same as 1 or less. Now this is obviously a weird way to write this for this example. But in the next video, when we are looking at a specific discrete random variable, this is a very useful idea. For this example though, it's very straightforward. There is only one value less than or equal to 1, and that is 1. So we get the same answer just in 2 different ways. And realistically, which method you choose to use is up to you. But again, if you have a lot more outcomes in your function, this could become a pain to do. This might be quicker. As I said, in the next video, what we're going to be looking at is a specific type of discrete random distribution, called the binomial distribution, which links with the binomial expansion in a kind of roundabout way. But thank you for watching.